are smaller, we should have like a higher frequency of like non-linear forces.
Why?
Because it's smaller and has more points of function.
But the more important factor is the total number of electrons. So electrons is more important. Okay, guys, shuru kori amra. Let's try to finish this. Let's see if I can get through it. I think we had this conversation. Tensile strength conversation. Just monrakba that when you are talking about metals being used in buildings and bridges and stuff like that, strong. Don't say the metals are hard. That's not the main property that we're using there. Okay, so let's start from here, page 27. So I want you guys to copy some stuff down. Most of this, like I said, is stuff you know. Just like this diagram. Did you copy this last class? Okay, done. So this is what the crystal actually looks like, but we will draw it like this, with the lattice with these lines and these dots. When you look at this crystal, you'll find some mention of this in your books. You'll very rarely find questions on the coordination number, but okay. But there was a lot that used to be taught in the past in older syllabuses. So I'm just showing you what I would do if I was taking the exam now, knowing the current syllabuses. So if you look at what I'm drawing, you have a blue sodium ion in the middle, right? And this looks like a square-based pyramid. And or niche, you have another square-based pyramid. So we call this square-based pyramid key and octahedron. So that is the arrangement around each sodium ion. So we say that sodium chloride crystals have a coordination number of 6:6. One sodium is surrounded by 6 equidistant chloride, and one chloride is surrounded by 6 equidistant sodium. Okay, so so I'm erasing this. I wouldn't be wasting my energy on this personally. But if you think how can both of them have 6? Jaman, let's look at the green dot here in this green dot. So if I extend this lattice like a bit to the left, right? What would there be there? There would be a blue dot. Agreed, Shaba? Now, if you see me make this base again, each chloride is also surrounded by what? By 6 sodium ions. So we refer to this as a unit cell. You'll find this in your books. I'm just to so that you understand how to deal with it. But don't memorize anything here. Just follow my lead and write one extra thing down here. So I'm actually like NaCl crystals have a coordination number of 6:6. Different crystals may have different coordination numbers, but details of these are not required in the syllabus. So you will come across the coordination number thing and the unit cell concept to a small extent. So the only one I would write down here is if I have CSCl, just like a short comment there. We'll come back to all this before your exams when we're doing question papers. Just I want it in the notes. So when you're doing your revision at the last moment, you guys are prepared for something like this. Okay. So if I remember it, you'll find this in your book in the ionic lattice section. You'll come across a few questions, very few. So it's not going to be like a big part or big focus for us. So if you think why is CSCl 8:8? When you can have 8 chlorides around it, because the CS is a bit bigger. So you don't have to worry about this. But when you see diagrams like this, let's say the NaCl unit cell. So I was showing this to the Cambridge batch as well last test. So this is when you talk about the unit cell, we talk about you'll see different images shown like this. They'll try to talk to you about that. I'm not finding an appropriate one here. Like this is cesium chloride's unit cell. You can see the image, or you can see the one there on the right hand side, the black CS and Cl. You can see how there's 8 around it. I just do something similar for you guys with sodium chloride, and you saw there was a key and octahedron over there. So my point is this is what we refer to as a unit cell. It changes for different salts. You don't have to memorize this anymore. You will find some mention of it in your books and very rarely in question papers. But these kind of things are not required anymore in the syllabus because we've just done away with all kinds of like crystal structure questions. Okay, let me just show you another thing before I get to my lecture. So you'll see there's different types of crystal structures that we see. Like if you see the image that I selected on the board, you can see the label there: cubic body centered, cubic face centered, and the other one got cropped a bit because I'm zoomed in there, hexagonal, right? There's lots of different crystal types like this. When you guys, those of you who will get into these kind of fields in the future, Jaipur University, you'll understand more. There used to be some of this in older A-level syllabuses. So I'll mention this just in one more situation when I'm talking about metals, because you'll see the image that I selected here. Look at the examples given below. You have silver, copper, gold, iron, vanadium, right? Niobium, chromium. My point is, this comes in when we talk about metals, basically. So if you're saying, why are you talking about this at all? I'll show you in a moment. So my point is, there's some factors that affect lattice strength that go beyond our scope. So the scope of Chiki, we just talk about the forces keeping them together. So coming back to the lecture. So what is determining Okay, so what is determining the force between the lattice, or when you're comparing two different lattices, let's say MgO. You guys did this last year in my GCSE versus NaCl. Last year when you wrote this answer, so you need to just highlight these examples. You'll see me doing a lot of these pro and con, A and B comparisons, A versus B. Because these are the kind of scenarios you should be prepared for. So if I'm saying that this is coming from Coulomb's law, all forces you study in chemistry are governed by this. Simple like a summary for you that works all through chemistry, right? Because all forces in chemistry that we talk about in high school are just electrostatic forces. So O-levels, you guys would have told me the ions have a greater charge. Now you add one more point to that. This one has a higher boiling point, the MgO. And then when they ask you, the charges of both ions are higher. If only one ion was changing, like say if we did MgO and Na2O, then you talk about only the cation. So the charges of both ions is higher. This was what you guys wrote last year as well. And all I'm asking you to add to this is the radii of both ions is smaller. So the radii of Mg is smaller. Radius of Mg is less than Na plus. This goes back to your chapter 1 summary of radii. They have the same number of electrons, both of them. They are isoelectronic, but the one with more protons is going to be smaller. And oxide has 2 shells. Chloride has 3 shells. It's period 2 versus period 3. So both factors, or when they give you those big questions where 6 mark asterisk wala question, if I give you an example where the magnesium ion, instead of magnesium, I give you, let's say, calcium oxide. Calcium ions are actually larger than Na+. If I show you the melting point of calcium oxide is around, let's say I'm correct, don't quote me on this, around 2515 or 2500. Sodium chloride is only 801. If I ask you to compare these two, you'll see the charge is greater, but don't talk about the radius of the cation, because talking the radius of the cation is actually larger in calcium. So that's going against the observation that we make. So you match the answer to the observation. You're saying, but why would I ignore it? Because clearly that doesn't have as much impact as the charge, the slightly bigger calcium ion. So they'll play around with these. Bonding and structure question shop, they'll play around with the variables. So this is why you'll see me constantly making these lists right? Or lists বা ধরো এই যে এরকম বা এরকম flow charts. So এগুলো খুব common questions. Get when you start doing question papers, when you start doing the workbook with me, get familiar with this approach. Constantly you're doing variable analysis, right? We're not showing any formulae, we're not showing any mathematical equation, but constantly we're checking your sense of logic when it comes to these variables. So we had this chat here as well when you guys were making these predictions, right? So let's wrap this up tale a chapter touch ke. So done shobai? Yeah. Which one? Yeah, we'll talk about the size of the oxide, but not the calcium. Not the calcium. Next, quick guys. So write stuff down. These are just random examples I'm picking. Maybe you might like the calcium oxide one better, right? As an example. So tomorrow modify the notes. I like this as my example to show you the changes from last year. But just slight modifications to your knowledge, right? So charge density is a term we came across in polarizing power and polarization. Charge density is a function of charge and radius, basically. So greater charge and smaller radius leads to greater charge density. So let's read. So in NaCl, opposite, so this is the structure answer. Like jara last year grade 10 notes gulo mone ache. With a grade 9-10 batch, I like breaking it down into like last year, right? I color coded the notes. So green was for key. Describe the structure. Blue was for key, the melting point, boiling point answer. Purple was the conductivity point. And orange was just something random from each structure, like brittleness is only talked about in ionic compounds. Malleability and ductility is only talked about in metals. So random actor information for each structure. So see if that helps, if you want me to do that again. But I took a different route for the A-level notes. I just wrote some stuff down, right? Because other information আছে like এখানে তো half page শেষ এটা, right? But there's a bit more we should talk about in some of these structures, for example them, right? So এটা ধরো is like a grade 9-10 version, but if you liked this arrangement and you want me to upload this, আমাকে বলো, ঠিক আছে? So my point is this: just mark it up, understand how you're supposed to write. I already wrote all this, right? So grade 9 থেকে শুনতেছো তোমরা এগুলা. Make sure you wrap all this up. So when you talk about structure, when the question asks you describe the structure of diamond, talk about the particles. Don't just say particles. Tell us which particle, atom, molecule, ion, egla bolba. Yes, and tell us the arrangement. Now, there's no arrangement in structures for AS chemistry except diamond and graphite. তাছাড়া কোনো জায়গায় কিন্তু যেমন we don't use words like tetrahedron, octahedron, hexagons. ওটা শুধুমাত্র কোথায় বলি? In graphite and diamond. So ionic crystals, I showed you there's a lot of geometry there, but we don't have that geometry anymore in our syllabus. So লেখা নাই, আগে থাকতো এগুলো যেমন metallic crystals, older syllabuses you had a lot of geometry in them. আজকাল it's like the grade 9 lecture I gave you. The positive charge next to negative charge. কোনো geometry দেখতেছি না এখানে. Okay, so I'd like to just understand these issues. Let's wrap this up, guys. So let's read. So this is what I would do. If you feel like আমার এটা লেখা উচিত ছিল, modify your notes. So structure, and I don't like dealing with the A-level batches ওভাবে আর কি, যে তুমি exactly এই বক্সটা লেখো, তুমি এই বক্সটা লেখো. That's like a more kiddish way of talking আর কি. Okay, now if you're saying না আমি ওরকমই করতে চাই, তাহলে করো এখনই, mark it up, right? Which one is the answer for structure? So what arrangement? If you're saying here, what arrangement are you teaching us here? All I'm saying is oppositely charged ions are held together by strong electrostatic attraction. And then when they say describe the structure, you must mention the type of structure. Giant, naki, simple. So these are usually questions that they don't ask because there's nothing to write over here. Next, each sodium ion. So this is where you might need to mark up stuff. Like I meant, this is the structure answer. And I'm the notes like this, so I wrote a paragraph here with some extra info. Each sodium ion is surrounded by 6 chloride ions and vice versa. Just hinting at that coordination number thing. This arrangement maximizes the attraction between Na plus and Cl minus and minimizes the repulsion between similarly charged ions. So why I talked about the unit cell is just to let you know, to give you that the perspective that you didn't learn all the factors at play here. So if you sometimes see some of your predictions aren't matching, don't get bothered by the like question paper. Tomake nutun information disi, right? And you saw that you thought the boiling point should have been higher. আমি তারপর তোমাকে দেখাচ্ছি boiling point of something is very low. Don't sit there and try to explain that, because you need to understand that there are certain things beyond the scope. So when they do that, they often want to do that to distract us. They'll give us something that doesn't add up, that doesn't make sense. Right? Why is this different? Like O levels, for example, we never showed you certain situations like aluminum chloride, the fact that it's covalent. We don't talk about that. But if we ever did talk about it, you're supposed to deal with it with the information given to you. Same process. Next. This arrangement maximizes attraction and minimizes repulsion between the similarly charged ions. Okay, strength, we just talked about this, strength of the ionic attractions. The ionic attractions get stronger with increasing charge densities. Charge densities is the term that is affected by charge and radius. So whenever I'm writing these answers, I prefer to write about the charge and the radius rather than talking about charge density. Because charge density of Mg is greater. Why is it greater? Because of those two underlying factors. So if you can get to the root cause, which is the charge and the radius in this case. Next, the radius of the smaller and more highly charged ions have greater charge densities and thus stronger electrostatic attractions. This explains why Mg has a higher melting point than NaCl. The radius of ions depends on the number of protons in the nucleus and the number of electron shells present. See page 7 for more. So the most important factor is what? Is the shell number. Once the shell number is equated, then you look at key proton number, then you look at electron number, if you ever need to equate a very rare situation. Next. However, if charge densities, so again, this is where we talked about this already. If charge densities become too high, you might be thinking melting point button thakbe. But actually, it doesn't even end up staying ionic. It ends up becoming covalent. So too much of charge density is a bad thing because the cations will be more polarizing. Okay, so there's there's a point where it becomes too much, basically. Okay, so however, so I wrote that here. However, if charge densities are too high, of the cations are too high, polarization of the anion electron clouds may occur, leading to increasing degrees of covalence in the crystal, which may lower the melting point. Okay, I'm not saying it will always lower the melting point. I'm saying it will. You saw the extreme cases we talked about. It may lower the melting point. Next, so solubility of ionic compounds. At a simple conversation korbo, I have something drawn here that I'll write around. To copy it. So when you're doing solubility, there's one simple thing you need to understand. Say if you look at this example. So before we read, first ektu lecture ta shesh koro and then tomader moto summarize koro. Okay, write what you want, what you think is necessary over there. So if you look at the example I'm going to show you, sodium chloride dissolving in water. Now we constantly talk about what in chemistry. Chemistry teacher that the lattice is key. Very strong, they have very high melting points. It's the number one message here in giant ionic crystal. Brittleness to beshi kotha boli nai. Conductivity is like a 1 or 2 minute answer. Most of the time, kono question ashte that why do they have a high melting point? So keep drilling that into you that they have very high melting points. Okay, so if they have very high melting points, why does sodium chloride dissolve so easily in water? Thanda panite dissolve kore, right? Sodium chloride. So why does it dissolve in water? Because when you have an ionic lattice put into water, what happens to it is, this is a water molecule, right? It's a polar molecule. So look at the V that I'm drawing on this diagram. Okay, so the V, the top end of the V, the pointy end of the V is key negative. The open end of the V is key positive. So just just stick to that one and try to understand what I'm saying as I explain this. So when the lattice is breaking up, you need to put in a lot of energy to break it up. We do acknowledge it's a key strong bond there. Because when you're making mobile ions, if they're actually mobile, they're not in a lattice anymore. So other attraction you need to get that energy from somewhere. But when we do this at room temperature, it dissolves, and it's not like the water is getting very cold. The water stays at room temperature. So where is the energy coming from? Now, you know it's a massive amount of energy because you know how high the melting points are of these compounds, right? So if I need to melt this compound, I need to we make it get to 800 degrees Celsius, for example, like sodium chloride. So thanda panite, how is this thing breaking up? What happens is that energy that's going in to break up the lattice is compensated by the energy coming out when the water molecules surround the cations and the anions, and they form these forces with them, leading to attraction, leading to a release of energy. This comes back to our fundamental concept in bonding. Any kind of bond formation. Bond forming both, I mean what? Any kind of attraction. Any kind of attraction releases energy. So even the attraction between the water molecules and the ions, or basically attraction korbe, energy chhalbe. So this energy that you put getting out from it, let's say you don't have to write these numbers. I'm just like book a number. Let's say if the energy is 1000 going in, but you're getting back 1000. তাহলে তো net তোমার কি কোনো energy দিতে হচ্ছে না. These kind of compounds are usually going to be soluble. Now we're not going to do math here, right? So how should we approach this? I want to do some math on the board because I wrote a sentence. I don't want you to memorize my sentences. I want you to understand the numbers. Anyone who's logical will understand the numbers better, and then you can write the sentence yourself, right? Because porikhar age you won't remember what I wrote in this page. Okay, so jara let's say struggle kore, usually they want to memorize what the books write, what the mark schemes write, especially boy manushgulo beshi focus thake on mark schemes, exact total likhte chai ora, because they don't know what else to write. So focus your idea on this. Energy is going in. You need some energy to break up the bonds, but you need to get that energy out. If you don't get that energy out from somewhere, then you have to supply that energy to break it up, like what you do when you melt it. Are you guys okay? So now let's say you guys could then argue with me and say we saw salts in IGCSE or in the lab, especially this year. You'll see a lot of these experiments in enthalpy chapter jump. You see a lot of experiments with temperature changes. So when you dissolve salts in water, they often absorb energy from water. Thanda hoye jay. So thanda hoye jay, refusing tale ota hocche keno. So let's say kotha amar 1000 lagteche bhangte, but I'm getting back 950. Tale what's my net? Plus 50. Now whether it's going to be soluble or not, you will memorize. Like if I ask you magnesium sulfate, is it soluble? You have it memorized, hopefully. All sulfates are soluble except lead, barium, and calcium. We'll talk about that again, book 2, the solubility chart and all that. So if we do the math and we see for a salt like magnesium sulfate or potassium nitrate, it's slightly endothermic. মানে ধরো তুমি স্কুল ল্যাবে potassium nitrate পানিতে dissolve করছো, এটা তোমরা অলমোস্ট সবাই করবা যারা ল্যাব ওয়ার্ক করবা স্কুলে. Potassium nitrate, they'll make you dissolve it in water, or ammonium chloride, one of these two salts, or something like that. And then you'll see find it ঠান্ডা হয়ে যাবে. একটু ধরে টিউবটা যখন ধরবা মনে হবে মানে ঠান্ডা পানি ধরতেছো বা ফ্রিজের পানি. বা when you take temperature readings so বুঝবা you went from 25 to 17 degrees কথা. And then they'll make you do calculations. We'll do all this in book 4 when we do an energetics, right? So তোমরা তখন you guys could then argue with me and say কি ব্যাপার এখানে তো endothermic process হচ্ছে, how is it dissolving? I'm just talking about this in advance so you guys don't get confused when you do all those experiments. So how can something that's endothermic dissolve? Because the water is giving it the energy. Water of the right? But what if it's something like this? যে ধরো 600 শুধু ফেরত যাচ্ছে, ফেরত আসতেছে, and there's a big amount of energy that needs to be provided by the water. So now in these kind of situations, when the energy gap is too much, the water won't provide that energy, and the compound is most likely going to be insoluble. Now the best part for you is you don't have to do any math, because your next question should be how high is this number before it's insoluble. That should be your next logical question. The limit bolte parbo na tomake ajke keno. When you guys get to grade 12, you will do a chapter like this called the solubility of ionic compounds, where like I just finished this with your seniors. Like eta tomader notes theke nichi. This is what we're going to read right now. And after I give them the recap of AS, jeta tomaderke ekhon porabo, then they start doing math, and the board is all numbers with them. And you're saying, to oder ki mukhostho korte hoy je kon point e giye jinishta soluble hobe? No one memorizes anything. It just follows some simple mathematical laws, and it's ultimately governed by a thing called entropy, which we'll talk about. I keep hinting at entropy because I want to warm you up to this idea that there's something more that we need to talk about. So when we talk about entropy, we make a decision based on one simple statement. If the total entropy change is positive, জিনিসটা soluble হবে বা হবে না. So as you get to grade 12, the কাজ for some of you মনে হবে কমে যাবে. Some of you will find it a nightmare, like A2 top version of your subjects, all your subjects. Some of you will actually like it better because you'll see some math, and then you have to count on the teacher. You get my point? So it comes down to math, and the people among you who are actually the proper science students, you will actually like it better. It's more difficult. You'll score lower, but I think the process is better. If you get my point, I don't know if you understood my point there, but this is a year away. Okay, so if saying what's your point, what would you do? I'm just talking to you like I would have wanted my teacher to talk to me. Like if you're saying what's your point, I'm saying if the energy gap is too much, meaning what? The bonds between the ions are too strong. Let me change some numbers here so it feels like I'm talking about different compounds. 2000. Let's make this 1600. I'm just randomly making up some numbers. So if the bonds are very strong and the energy, the attraction, meaning the ionic bonds, and the attraction with the water is not that strong, it's not releasing as much, that gap might not be covered by water. There's a law, mathematical law, that governs this in the universe. It's like, this is where the analogy has to come in, because I can't show you the math. Let's say you're going out to eat with a group of friends. You guys decided, you guys, you have a budget. There's this buffet or whatever, and your friend was short by like 50 taka. So you have to cover for that person, koto. Or 50 taka dite hobe. So tumi probably diba. Right, or maybe now dite paro tumi, depending on you. This is where the human analogy breaks down. Because আমার এই কথাগুলো might not be applicable to you. যেমন for example, let's say তোমার 1000 টাকা আনার কথা, তোমার friend 0 টাকা আনছে. Some of you say তো ব্যাপার কি আমি দিয়ে দিলাম ওর জন্য আজকে, ও পরের দিন দিয়ে দিবে আমার জন্য. But let's just say in this situation যে তুমি খুব হিসাবী, right? And তুমি 1000 টাকা জানতে আমরা খাবো, তুমি আনো নাই কেন, যাও আজকে খেতে পারো না তুমি, right? So there's a limit যেখানে তুমি your limit will break. But let's say it's not a close friend, it's like an acquaintance, someone new you met, but you don't even want to hang out with them. Right, and এটা obligatory একটা অফিস থিং, ধরো যাইতেই হবে, আবার যেতেও হবে, যেখানে যেতে যাচ্ছে না আবার টাকাও দিতে হবে ওর জন্য, যে না আমি দিব না, right? But so this is where the analogy kind of breaks down, because in the universe is a mathematical law that governs this, unlike human behavior, right? So coming back, energy gap টা কম হলে the universe can cover for it, as in the water in that case, the surrounding. Energy gap টা বেশি হলে it can't cover for it. Right, so I tried to write that in simple English. It might not look like the same thing. Okay, so let's read the summary. Then you guys copy this rough work. Are you guys okay with what I did here? Opposite charges attracting again, and chobi jon aakte holo tomaderke ekta chobi aakte bolbe. I'll show you what that is. You'll have to draw a thing we call a hydration sphere. So let me just read this paragraph. Tomra dekho, if I etkon je bujhalam 10-15 minute lagse amar, I wrote this in 3 lines. Okay, please to see if this works. When an ionic solid dissolves, the lattice must be broken down, and this requires energy. This energy is compensated for by the release of energy when the ions become hydrated. So this is what we refer to as a hydration sphere. Basically, I'll show you a diagram you have to draw, because a colored image for the whiteboard. But tumi porikha din ki aakba. You could just draw this, but I'll show you the black and white version that I would draw if I was a student. So hydration sphere, what's happening here? These dipoles are doing what to each other? These dipole and the ion is key. They're attracting each other, and that releases energy. We call that the hydration enthalpy. You'll see I wrote the text in such a way so I didn't talk about the names of the energies. What a great 12 Shikpa. The hydration energy, and that is called the lattice energy. So tomorrow is in and out bolo. So energy lagbe bhangte, and then I'll get some back when the attractions form. So see if I capture this. The ions get surrounded by water molecules, resulting in the formation of a hydration sphere, which you will be asked to draw, guys. So you can see how the lattice is getting surrounded by the water molecules, and then you end up forming these hydration spheres. And then I wrote something here. When a hydrogen sphere is formed, you have to describe this. Sometimes someone can bolbe, oh, je 6 mark asterisk wala answer. How is this dissolving? Why do ionic compounds dissolve? When hydrogen sphere is formed, oppositely charged dipoles. See how I'm talking about the particles? Like whenever I talk about a force, I'm talking about what has the charge. So oppositely charged dipoles in the water molecules. I didn't just say dipoles in the water molecules. I'm trying to make it sound like opposite charges attract. It's খুব important in these A-level answers. Okay, man, it's your syllabus requirement. So they are attracted to the ions by name of the force, very simple name, descriptive name, the ion dipole force. Ion or dipolar mode. The energy released, this is the summary of the lecture. The energy released during hydration is used to break the lattice. If the hydration enthalpy is not exothermic enough, man, I didn't get enough key out, not exothermic enough. If the hydration enthalpy is not exothermic enough to break down the lattice, then the ionic compound will generally be insoluble. I'm not saying this is the final explanation. I'm saying this is what my summary would be if I was taking the AS exam in 2025. Okay, clear, Shobai? So, tumra ekটু এগুলা একটু লেখো, write something, please. If you want me to repeat something, bolo, and then I'll add the hydrogen sphere ekটু তাড়াতাড়ি করো, and let's wrap this up. So you guys will have to be able to draw a hydration sphere. This is the only new thing for me. If I was revising পরীক্ষার আগে, as a teacher, আমার আজকে সব বলতে হবে, right? আমি বারবার তাই এই কথাটা বলতেছি, কোনের জন্য তো এগুলো লাগতেছে না। Like ionic compounder অনেক কিছু আমি না পড়লেও তোমরা কমপ্লেন করতে না, but I'm just assuming কারোর কিছু মনে নাই for the benefit of the weaker students, okay? So তোমরা যারা বুঝতেছো যে হ্যাঁ সব এগুলো পারতেছি মোটামুটি, you're very confident, highlight the things that are new to you, যেগুলো তোমার কাছে নতুন লাগতেছে। পরীক্ষার দিনে কি লিখবা, সরি পরীক্ষার আগে কি লাইক কি পড়বা, ওই জিনিসটা একটু হাইলাইট করে রাখো। Yeah.
What would be a definition for hydration?
লাগবে না, ওটা এসে শিখবা, এইটুতে শিখবা, বাট তুমি এভাবে বলো, is the energy, just say it's the energy released when water molecules attract cations, oppositely charged cations, right? But আমি কেন মানা করতেছি তোমাকে definition, like if you ask me for it, this is the definition. You don't want to study this today. If you're an AS student, this is the definition. It's the enthalpy change on 1 mole of gaseous ions is dissolved in water to form a very dilute or infinitely dilute solution. So it's overkill for us. So আমরা এটাকে বলবো কি, we'll just say it's an attraction. যেমন তোমাদের A2 senior দেখো যেটা বলি, এটা একটা attraction, so it will, মানে this interaction is an attraction between ion and water molecule. So there must be energy being released because bond forming is exothermic. ওইরকম একটা summary লেখো, right? So the extra stuff you don't need to remember from there. Okay, so I'm going to add the hydrogen sphere to the board. So let me just draw it again. So the upper part hoise, the blue, the rough sketch. Eta aঁকতে না চাইলে, if you feel like the notes did a good enough job there, koro, but you have to draw the hydrogen sphere. Okay, so can I scroll down? So I'm making a hydrogen sphere to aঁকতেছি. So if I was you, for me, the hydrogen sphere, I would draw it like this. So let's say a cation in a hydrogen sphere, and then anion in a hydrogen sphere. So normally the minimum you'll see in mark schemes, I'm scrolling down, tell me if I need to move around, guys. So normally when they ask me to draw this, let's say if you wanted to show sodium chloride, যেটা আমার example sodium chloride নিয়ে, minimum ওরা বলবে 3টা water molecule আঁকো। Normally we draw up to 6. I'm saying কম আঁকবো কেন, সময় কম লাগবে তাই কম আঁকবো, right? If the examiner wants me to draw 3 minimum, আমি কেন 6টা আঁকবো? And generally you don't want to accommodate more than 6 because there's some issues when it comes to fitting so many of them in that small space. Bigger ions can attract more water molecules, particularly on the syllabus by. So I don't want to overthink this. Saying, what would you do? So I'm just showing you what I would do today if I was in class. I told you the requirement is minimum 3. I mean, our notes, I would write 4 here today. Tomorrow koro. Ako, I need you to practice these because question paper it's like a lottery. Question pabona ki pabona. Okay, so just wrap up your notes properly. Whenever I show attractions, I should always show the opposite charges. So I should show what are the opposite charges here. The delta, which I'm pull right? Ulta hobe. Can I make chloride di? Because I showed the plus next to the minus. So instead of erasing the whole thing, I'm just going to take a minus square this, guys. Delta plus, delta plus, delta plus. Think সবগুলো লিখতে হবে, yeah. So you just want to surround them by water. They also sometimes call it a hydration shell. Online sources especially, it's like a shell of water molecules around it. I'd go with this term. This is the preferred term in our syllabuses. So these hydrogen spheres, when they ask you to draw it, they basically show the examiner that, okay, that opposite charges are attracting. And if you're saying it's obvious, it's just like they want you to show that you understand the nature of the electrostatic force. And again, it's not my opinion or anything. I'm just saying it. Excel is a bit paranoid when it comes to you not saying oppositely charges. You will see opposite charges attract each other, even if you feel it's obvious. Okay. So they want to check and the mistake most of you tend to make when you draw these when you write these answers is you guys end up saying in water there are hydrogen bonds. You won't get a mark here because if you say between the water molecules there are hydrogen bonds. Okay, because in water, what do you mean hydrogen bond? Do you mean between the atoms, between the nucleus and the electron? What do you mean? Because there's so many different forces in nature. And then Na plus. So I'm going for minimum. I'm going for 4 in my notes. When you're doing your question papers, J3 is usually what they say. That's why my diagram in the notes has 3 there. The graphic that I put in my notes. So delta minus. A lot of online sources, when you Google this, if anyone does do a Google search and you try to see what like an alternate source of the information, a lot of sources will tell you that there's always 6 around the water molecule, around the cations. You don't have to remember that because it's not in AS. If you want to draw 6, Ako, I'm just saying, why would I do the extra work as a student? Okay. Saying, why would they talk about 6? It's because there's something else that happens when the water molecules attract the sodium ion or any cation for that matter. Some of you already read this in the notes probably. I told you to skip past it, but dative bonded, jara hydrated ions name porso, you will have to come across it. So you'll do that in A2. So even in A2, if a student asks me in A2 papers, draw the hydrogen sphere, same জিনিস আঁকবো তোমাদের জন্য যেটা আঁকতেছি. Ignore me trying to make it look neat. Okay. পরীক্ষা দিনে don't waste time on all this. But I'm just trying my best to করা যায় for the whiteboard. Neat করা. But doesn't have to be neat. Just scribble it down quickly on exam day. If you're এতগুলো ও লিখতে চায় না. If you're feeling lazy, ধর minus এরকম করলা, and then label the water molecule. Okay, water. Delta plus, sorry, delta minus delta. Okay, I mean minus negative charges and then cation or anion. But don't just draw a random V and assume I'll understand you. Label your symbol. All right. So obviously, if this was my exam and I had the time, I don't want to take a shortcut. Okay. So let's not write the shortcut today. But let's say you're running out of time and tomar 1 minute baki. Okay, right? So again, don't waste so much time that for a 2 mark or 3 mark answer, you end up spending 6 minutes. Right? So don't make it too neat on exam day. Okay, we just want to see that opposite charges attract. Some of you might say you're wrong. Depend if you want to show this, like what am I showing? I'm showing the attraction. So let's put this in some lines there. Because sometimes they'll tell you draw a hydrogen sphere and label the name of the force formed between the two. তখন বলবা ion dipole force. No fancy name, no like specific name, just a descriptive name. Force between ion and dipole. I'm sure regular MCQs আসবে. Which of the following statements is true? And they'll ask you to describe the force. So আমি দেখাতে চাচ্ছি আজকে in my whiteboard. If saying এটা না দিলেও তো হয়তো true. When they tell you to label the force, তখন তুমি বুঝবা they want you to label the force. Then I'm sure you'll all label it. So just imagine যারা 6টা আঁকতে চাও, gets a bit crowded. Okay, it becomes difficult to show. Is everyone okay? So these are hydration spheres. So most of the diagrams I'm making you draw or forcing you to draw are basically stuff that you'll have to draw in exams. Okay, so like the ionic lattice data. Okay, so tomorrow just পরীক্ষার আগে put down a summary, a reminder for yourself. যে পরীক্ষার আগে যেন তোমার মনে থাকে যে কি নিয়ে আমরা কথা বলতেছিলাম ক্লাসে. Okay, so give me just one more minute. Let me just edit this too. Right. So moving on. So these are the hydration spheres. I'll just label this for people who look at the board for it. Okay, and finally, right. So I'm moving past this. If everyone's okay. Physical properties of ionic compounds. If you don't know this, you should not be taking A levels. Is my opinion. Okay, so force, energy, structure. Don't say molecules in this answer, please. Like the NaCl molecules are held together by. Please don't say molecules. So the strong electrostatic attraction force between particles, oppositely charged ions, held together in a giant structure. How do you know when to say giant? So I put structure for second. How do you know when to say structure? When the question says in terms of bonding and structure, right? Normally we just separate force and key, force and energy, right? So a lot of energy is needed. This is like a bonus mark because if I know the force is strong, then obviously I need a lot of energy, right, to overcome the forces. Electrical conductivity doesn't conduct in the solid state, because the ions cannot move. Don't end up writing an essay when an Excel gives you 6 lines. Well, why don't they conduct in the solid state? They want to hear the idea of movement, right? Just remember that. Conducts electricity in the liquid or aqueous state because the ions can move. Highlight these things blatantly. Don't say free. Free doesn't mean the same thing as moving. Right, so electrical, you guys all did this in AS, IGCS as well. When liquid or aqueous ionic compounds conduct electricity, they act as electrolytes and undergo a change called electrolysis, which you learned last year, but you don't have it again this year in AS, or ironically even in A2 almost ashana. Once in a while ashe A2, but beshi ashana. But if I ask you something about electrolysis, you can't complain because some of the IGCS students chilla. Right now, if you're saying it's unfair, I'm just saying it's like if I ask you something basic in math that you did in grade 6, complain korbana. You get my point? So they don't do that too much. I'm just saying you can't complain if they do. And finally, brittle. Layers of ions cannot slide. 1 mark, because the repulsion between similarly charged ions causes them to break apart, right? When you hit them, they can't slide, unlike the metals that you see after the break. So when you apply an external force, if you try to make this layer slide along, it moved, it shifted out a bit. It can't roll, the layers can't roll over each other like the metal layers. That's why metals are malleable and these aren't. They break when you hit them hard enough. Okay, so the like charges would repel. Okay, they almost never ask you to draw all this English notes, so this is to make it a bit more visual. If something is brittle, reminder of what brittle is. It will break or shatter when a stress is applied to the structure rather than be deformed. Which is what metals become, they get deformed. Materials like glass and ceramic are said to be brittle. Okay, so that's it. Ionic lattice done. Break it for, we'll get to the next 2, hopefully. Let's continue. So yeah.
When stress is applied to vitamins, when stress is applied to solid layers baseline of each other, that's when fluorination happens.
Yeah. So what I mean by cannot slide, this is the point they expect in the mark scheme from you, that it cannot continuously keep on sliding, because as soon as it slides a bit, it to move করছে তখনই break করবে, right? Whereas the metals, you'll see they can slide like continuously, like it can move along a lot, right? So they usually expect that from us. Okay, এখানে বলবো cannot slide in the mark in the answers in the exam, and next to the বলবো they can slide. So this is nothing. Next one, there's nothing different compared to IGCSE here. So this should be easy for most of you. Rafi has a question from the book which he posted in Google Classroom. Just check. Okay, so let me just bring in this to the board. It's about polarization. তোমরা এই জিনিসটা করতে থাকো, like from time to time books এর comments গুলো যেগুলা পড়তেছো, bookmark it, screenshot it, right? Send it to me in Google Classroom. তাহলে class and we can have these conversations. So Rafi কোন line বললো as I read this. Okay, so the ease with which an anion is polarized depends on its charge and size. Anions with a large charge and a small size, wrong. It's a large size of it. That's a typo. Okay, that's a typo. It'll be large size. Okay, sir. You'll find a couple of typos. Okay, and in an ionic lattice, the polarization of anions creates some degree of sharing of electrons. Yeah, okay, fine. So large size of it. Okay, this is good page, Rafi. Large, page 70. And there's a few typos. It's a new book, and it's not new, but it's the first edition, and actually typo quite a jagay papa. So if you ever find something like this, let me know. So guys, page 70 there, if anyone like Jara Basha, so right, or if you want to write this down somewhere, but make sure you understood the concept, and you'll be fine, right? So large size of it. Okay, moving on. Yeah. We don't really talk about that at in AS chemistry, but infinite distance meaning it's not influenced by the nucleus anymore. No attraction at all. The atom lost that electron. It became a cation, right? So like when you do this in physics, correct me if I'm wrong, see if it comes from something like this that you saw. Like lines that way. Was it something like this? Like, let me just draw it. Like erum kichu dekhchila, where they showed lines, and then these are energy levels of electrons. You'll find this is a very common way to describe the energy in electrons. So you'll see the gap between the lines is gradually decreasing. Ekta pointer, you'll see they label the last line. So let me remove the last one. Let me just keep this many. They label this last line as infinity, meaning it's going further and further away from the nucleus, right? So 0, this is the ground state, this is the normal state. Tapor 1, 2, A2 physics like when you talk about how ionization energy you just removed an electron from the atom, right? So physics teachers they won't use the term ionization energy. They'll talk about the energy required to make an electron escape. You'll come across this in a topic called A2 the photoelectric effect. Like if I remember right, this experiment was one of the reasons when Einstein got one of his Nobel prizes, right? Proving this, and this proved that energy, when it's being streamed to us, like this light that's falling on you, it's not coming in a. We know it's a wave, right? You know that light has electromagnetic waves, electric and magnetic component. But these waves are not a constant stream of energy. It's like more like they're shooting packets of energy at us, discrete packets of energy. So a frequency of light has a particular amount of energy in it. So the packets of energy coming from violet light is greater than the packets of energy coming from red light, let's say, on the spectrum, or gamma rays and radio waves. So you'll have physics porba. If you ever come across this anywhere, you'll see on chemistry books when they try to explain ionization energy to you, right? Okay, moving on. So guys, next, giant metallic crystals. So I didn't change anything here. I'll just make one comment which links to this. যে কার boiling point এখনই করে ফেলে, কার melting point বেশি হবে, সোডিয়াম নাকি ম্যাগনেসিয়াম among the metals? ম্যাগনেসিয়াম কেন বেশি আর radius কম, তাহলে অ্যালুমিনিয়াম should be more than কি magnesium. So saying where will you do this again? But so I'll do this again in book 2, which will be starting very soon. Book 2, there's a chapter called the periodic table, where we'll talk about periodic trends in melting point that you'll have to memorize, by the way. You'll have to sketch as well. And there's a new thing in the syllabus. They want us to learn about period 2 as well. So you can see the increase in the melting point from sodium to magnesium. You can see the increase from magnesium to aluminum, but isn't the increase smaller? So then you might ask me, sodium to magnesium, a massive jump, because the charge doubled. And when you're going from magnesium to aluminum, the charge increased by 50%. So it's a smaller percentage increase in charge. It didn't double. That's not the full answer though, because there's more about the crystal structure that we can't talk about. So that's why I showed you crystal structures before I got into the lecture. So they'll never ask you that. They'll just ask you to explain why is Mg more than Na, why is Al more than Na, right? Once in a blue moon, every 5 years, you'll get a question. Why is the increase from Mg to Al smaller than the increase from Na to Mg? We'll deal with this when we come to this in book 2, at the beginning of book 2. So let's go in the sequence. I wrote it here. So same factors always, charge and radius. Even when you talk about intermolecular forces, which dipoles attract more? The ones that have greater charges. So same kotha. So let's read with that in mind. So the delocalized electrons, I'm going to copy something from your grade 10 board again. Tomorrow to copy kore now. Saying what is this? I want you guys to be able to draw this in the exam. Now, what will you draw on exam day? Like last year, so so I didn't put a space in the grade 10 notes. I used to put a space. Board in the grade 10 notes, I used to put a space like what to draw in the exam. Right? Since you guys are A-level students already, 3 bochor dhore portecho egula, I'm assuming like this gets the job done. Okay, I didn't give that level of instruction here. Okay, so so what do you want us to write? A-Tech to copy kore now. The sketch in the exam, like porikkhar dine, what I would draw. Okay, to please phone guli silent koro. I'll ask you to leave if you don't understand this simple rule. Right? So magnesium lattice label your symbols always. Okay, red dot, so what it is. It could be an atom that you're showing me. So you label the dots and the symbols you're using. You're saying, why do you have to label the plus? Plus like আমি কেমনে বুঝবো তুমি cation mean করছো? You could have meant a proton. So if you think, but obviously I meant a cation. Don't give them a chance to penalize you in the exam. Okay, you're saying, what if I wrote +2? They'll accept it in a lot of cases. I'm just saying, why would you want to take that risk if you're doing this on your exam day? Right? Some people write it like this, Mg2 plus. Okay, don't take this a manlam. Don't boost to say you meant Mg2 plus. But I'm just saying, if you're saying, what if I just write plus? You're not telling me that charge is +2. You lose a mark. So hence you label. I like this version. If you guys want to draw Mg2 plus in the middle, some people like drawing electrons, E minus, E minus, E minus. If you think, hey, it's better like this, okay, koro. If you feel like that's saving more time, like Jara usually labeling they feel like this is a waste of time. I'm writing electrons 12, 24 times, or 10, roughly quite a 24 dot, like, or let's say rather for 9 atoms, I should show 18 dots. That doesn't matter. The number doesn't matter. But instead of writing E minus, E minus, E minus, 11 bar, ba 12 bar, ba jotoguli dot like so. Just label it once, right? That's a smarter move, okay? Okay, so whenever you use dots and symbols, like when I draw diamond, they don't make us draw diamond, Ajkal. What is this dot? I'm the what you mean. So I'm bolba either label korba ba pashe put a key carbon atom. Okay, so just whenever you draw any diagram, make it clear to the person checking your script. Done? Shall Next. So the delocalized electrons are the valence electrons of the atoms. They can move around throughout the structure, and this is what gives metals their good electrical conductivity. In metals, this is the structure answer again, right? Like the first paragraph is always the structure answer in these notes. So again, if you feel like that's not obvious, like, so if I ask you to describe this, to me, I'm okay, arrangement of particles, there's no geometry. So I'll just say, mention the particles and talk about the force. There's a giant lattice of, so giant vector cation cation, lattice of I think lattice is important here. I'm telling the examiner that it's not moving around, it's in a fixed geometric arrangement. So I'm using that technical term to save some space. I have to write less. A sea of mobile delocalized electrons. You must use the word delocalized here. There is strong electrostatic attraction between the cations and delocalized electrons. Okay. Next, alloys are mixed. What are alloys? Alloys are mixtures of metals. A lot of people think they're mixtures of metals, but they're mixtures of metals with other elements. One, a metal plus metal or metal plus non-metal. Alloys tend to be harder and stronger than pure metals, which makes them very useful in some applications. In most cases, it's more useful than the actual key, pure metal. Guys, are you okay with me not explaining how they get delocalized? Are you guys all okay with this? Okay, like, so moving on. So they're harder and stronger than pure metals, which makes them more useful in most applications. Even in jewelry, we don't want to use 100% pure gold. We want to use a mix of gold. But like when you hear about, say, I'm using gold as an example because you might understand this, 24 karat gold, but that's like very pure gold. Most jewelry that we buy is like 21 or 22, or Bayre, it's even less in other countries. Some of the 21 karat popular, but Bayre it's even less, like 18 karat gold. So they mix the gold with other metals and they alloy it, basically. It becomes harder, right? So it doesn't bend, scratch easily, doesn't dent easily. Laptops and iPads and phones on any device that has aluminium, it's not pure aluminium. Because pure aluminium on it easily scratched, right? The border of your phone sometimes, right? If it's like they used to use stainless steel at the time, if you're thinking of iPhones, then they moved to aluminium. Then they moved to right now the higher-end ones are titanium, right? So titanium has its benefits, but all of these metals they use are alloy because, and you'll see when they talk about the aluminium, like when you look at Apple's releases of the product release, you'll see often they'll talk about the aluminium, how it's scratch resistant, and they'll use big numbers like to dumb it down for normal people, like 7,000 aluminium, which means like nothing, right? Agar version chilo 6,000. So they try to make you understand that right? 7,000 ki. As a science student, I'm thinking it's more scratch resistant, it's more alloyed, it's harder. You'll see another thing phone reviewers do with phones or big tablets or big phones. They try to bend it, right? The bend test. The bend test, I think, started with, I forget. I think iPhone 6. iPhone 6 was the first big iPhone, like proper big iPhone. iPhone 5 was still small and narrow. 6 was like the bigger one. And what used to happen was when people put in their jeans, shamner pocket or piche pocket, and you sat down, it took a tap khache phone, right? The phones started to bend, and no one ever saw that happen with the phone ever. And there were a lot of complaints about the phones. Apple being Apple, they said, "Tumra bhul kartecho. You're putting it wrongly in your pocket." But excuse this, right? So that after that, they call that event, I think, Bendgate. a phones. After that, you'll see all phones, they tested to see the aluminium used probably in that phone was not alloyed properly. So it wasn't as hard or stiff. So the more harder you make it, it won't bend easily. Why does it not bend easily? Let's explain. So, so this extra hardness is due to the different sized atoms. These highlighted bold font points are what I would write in the exam. I can't just write a mark scheme in my notes. Like about the sliding thing. That is what I would write in the exam. Right? So when you're reading before your exam, exam when you're doing a revision, I tried to write it like a mark scheme, but I wanted it to feel like you're reading a set of notes, right? I didn't want to make it feel like a mark scheme. So, but that's what I'm trying to hint at. So why is it harder? Because the different sized atoms, not allowing the layers to slide as easily. And the lattice is, if it's a 3-mark answer, lattice is less regular, right? Less uniform. Okay. Steel is an alloy of iron and carbon. You must know about steel. Brass is optional. Brass is an alloy of copper, and you must know about steel though, because you learned about it last year. Next, pure metal. The layers can slide over each other relatively easily. I'm not saying they're all soft. I'm just saying it's softer. Soft manaki, scratch test, right? So they usually get scratched more easily. They bend more easily. Like this grill behind me. Like I'm pointing to the window grill that we use Bangladesh behind me. Grill gulo, would you want to use an alloy with a lot of carbon, steel alloy with a lot of carbon, or pure iron? I'd want to use a lot of carbon because I don't want this to bend. So this is meant to stop people from breaking in. So if it was bendable, they would be able to break in more easily, right? So alloys, therefore, usually tend to always be more preferable. But when you make a car body, on the other hand, you don't want the car body to be too rigid. You want the car body in a high-speed crash to crumple in the front, like a Coke or Pepsi can. You can crush it with your hands. You want that to happen to the car. If you think, but it is counterintuitive. Why would I want that to happen to the car? In a high-speed crash, you want the car to act like a shock absorber, the front end of the car, right? Next, so this big atom here that you see makes it more difficult for the layers to roll, basically, right? They get atka jai, basically, so you can can't like move as easily. So next, physical properties of metals, high melting point. Why? Again, force, energy, and structure. I wrote structure second here in these notes. Strong electrostatic attraction. Look at the formatting in the sentence, right? You don't have to write my sentence. You have to hit the points. Name of force, strong, and particles. And I didn't just say ions. I said cations. I didn't just say electrons. I'm saying delocalized. Because not all electrons. I'm only talking about the delocalized electrons. Held together in a giant structure. A lot of energy is needed. Group 1 metals are a bit weird. Some metals tend to show unusually low melting points. For example, group 1 metals, because they have the lowest charge densities. And down the group, what happens? The cation is getting bigger. The melting point will keep. Cation is bigger. Charge density, attraction, that's why you remember in grade 10, you used to learn group 1 melting points. Down the group, melting point keep decreases. So I usually book 2 if you feel like I should have written that down, like the paro, right? So group 1 metals tend to have low charge densities and fewer delocalized electrons. I think let's write that point down, okay? Because you won't remember the book 2 put on a book 1. So down the group, cation radius increases. In other words, charge density is decreasing. If charge densities are decreasing, so you should comment questions are key. So the O levels are most of A levels are explanation deva. Charge density is decreasing, so the electrostatic attraction decreases, and therefore the boiling point for group 2 as well. Same jinish to hobe na. So boiling point or melting point or both decreases. Okay, so a pattern and answer. And across the period, we talked about what melting point is increasing in charge density. Next, electrical conductivity. Metals are good conductors. Again, 2-mark answer. They give you 4 or 5 lines to write this answer. Can I just write these 3 words here? Mobile, delocalized electrons, or delocalized electrons can move. 4-mark answer. You don't write an essay there in the exam. Next, malleable and ductile. Again, the layers of cations. This is usually a 2-mark answer. 1 mark for this. Can slide. You might say, how is this a 2-mark answer? I'm just letting you know, it's often a 2-mark answer. If it's a 1-mark answer, I'll write the same thing, right? If it's a 2-mark answer, bonus for me. I'm getting an extra mark. Metals can be beaten into different shapes. They're malleable. They can be beaten into different shapes. They're malleable because of this reason. When you apply force to a metal lattice, what happens? The layers can slide because the electrons are mobile, unlike the anions in the giant ionic lattice. So the layers can slide around and therefore it can deform. Okay, so next. Metals can be beaten into different shapes. I'm just defining the terms again. That's malleability. And drawn into wires, that's ductility. And stress is applied on the structure. The layers can slide with the delocalized electrons always staying in between the cations. So they act like that glue holding it all together, because the glue, if you get my drift, is mobile, unlike the anions, which are rigid. High tensile strength, I didn't explain anything in this. They won't ask you to explain anything in this. I just wrote something in italics here. This property cannot be fully explained at this level in chemistry. Physics, so you'll learn more about all this. However, it is important to know that this is one of the properties that makes metals useful in construction of buildings, making aircraft bodies, car bodies, etc. Why do we use metals in buildings? They're strong. They add strength. Don't say hardness. Next, simple molecular. So simple molecular main kaj is chapter 4. Chapter 4 the butcher, right? The intermolecular forces. Keep memorizing these blue boxes. Okay, the summary points. Make this a major objective. So let's read on. So I went for some examples here. O levels let me just show you your board. This is the first time I asked you this ever. This was way back in grade 9. None of you had any idea what I was expecting from you. So this was like 2021, or maybe 2020, whatever, 2020 something, right? These were your first answers, this group of students. Almost every group of students tells me the same thing. I'll show you what your juniors did this year. H2O, CO2, when I asked you, saying, what did you ask us? I asked you, give me examples of simple covalent. So, right, so water bubbles, CO2, methane, someone said glucose, which is rare in a grade 10 class. And then some of you, these are the Southbridge students who do this every year. Only the Excel batch grade 9 students talk about organic molecules, because I think in Southbridge they do some organic chemistry with you at some point, right? So these are usually the Southbridge students in the group who are saying this, but most students are thinking of what? Molecules with 2, 3, 4 atoms. And then when I highlight that to you, molecule, if you ignore the organic example, ekta molecule with more than 5 atoms. Methane is the highest, if you ignore ethane and glucose. Then when I ask you, you guys don't get stuck. Every grade 9 batch is the same from the beginning since I've been teaching. Okay. And I asked this question because I want you guys to understand, because I realized this in A levels, time. Simple molecular doesn't mean small. I used to think simple one is small, right? And then when I asked the batch these questions, C60 simple or giant? Most people say giant. If some people first say simple, most people say giant. Then I increase the number a bit. And then when I show them C100, 202, more people get converted and they say giant. I'm just telling you your psychology here. And if I still see a lot of people saying simple, then I'm going to barabari kori with the grade 10 batch. C200, H402, then everyone says, giant. It's like you, and then I ask you, why did you say giant here? Because it's like you have a threshold in your head. Eta upor gele, eta giant. But what's the threshold? Who taught you the threshold? Right? So I just want to see tomader limit. So if you look at your counterparts right now, 2 years younger than you, what are ki bolche dekho? The notes are formatted to change, sir. I put it into the notes. The last year I gave you guys these notes. These were their first examples. So similar to you guys, right? This is again the Southbridge student, right? These are I always focus on, I tell students to focus on this. This is your top of mind recall. And this is what you're subconsciously thinking of when I say simple covalent, right? You might say now the first 2 rows, yeah, but my point is the first set of samples, because usually the batch slows down after this. Then I keep pushing you, arabolo, and then some people look at the periodic table. When someone thinks of fluorine, someone starts saying bromine, iodine, chlorine, and so on, right? So my point is, if you what are you trying to say with this to us? I'm saying when you guys are thinking of simple covalent, don't think of small. The word doesn't mean small. I know giant means big, but simple doesn't mean it's an antonym of giant. It sounds like that when we look at our thought processes. We're looking at small molecules here. You need to understand this chair, for example, that you're sitting on. It's made up of thousands of atoms in one chain, polymer. That's a simple structure. So how do you know it's not giant? Melting point to beshi hai na eglar. Giant jodi hoto, it should be like diamond type melting. Diamond is one of the highest, 3600 degrees Celsius. Same carbon atoms. Okay, manlam ekhane hydrogen ache, but tarpor it would be close if it was giant. Or let's say at least 1000 to dhorte parbe. It smells at 120 degree polythene. So that implies what? It's like a key intermolecular force. If I ask you what intermolecular force, London, PD, or hydrogen bond, depending on the polymer, to me decide. Are you guys okay? So simple doesn't mean small, but giant does actually mean big, because it's a massive number of atoms that are bonded together. Right? Next class, when I draw this diagram, this is you guys saw this diagram last year as well. When I draw this diagram in grade 10, I show a cloud over the thing, the layer of graphite. This is what graphite looks like from the side. If you think, what is it in reality? It's a pi bond. Those electrons, the fourth electron of each carbon atom forms a pi bond. So pi bond kibhabe thake? Above and below. We call it a delocalized pi bond because it's not localized over 2 atoms. Okay, that's the only new thing in this chapter left. So I might run out of time today to do this. Let's see. So moving on, let's come back here. So think of that. I didn't write all that in the notes. I didn't ask that to you guys today, but just think of that. Your thought processes often are thinking of these small molecules. That's why I put one of these in the examples here. C60, Buckminster fullerene. It's a type of allotrope of carbon. It's referred to as fullerenes. This is a specific type of a fullerene. There's a lot of fullerenes in nature. Like there's fullerenes that look like this. Like when I give students these kind of questions, they often think these are giant. Like if you look at the fullerenes in nature, there's many different types of fullerenes. Let me find an agitator. Let me find one where the text is clearer. C24. Oops. There, let me just. So when you're looking at fullerenes, you can see there's many different types of fullerenes. There's all these spherical kind of ball-like structures. We focus only on the C61. That's the one they show you in the books. You should expect, if I ask you of any of these questions, that these are simple molecular. Saying, how do you know? They have a fixed number of atoms. That is what you start with. What is simple molecular? Not small. Simple molecular. Then you're trying to set an imaginary threshold. Small molecule. Small ki mane 60, na 70, na 80, na 100, na 200, na 3, na 4. It's all subjective. Right? You can't say small there. You'll say, when you have a fixed number of atoms, even if it says C6000, simple. Because you have fixed number of atoms. Diamond formula key, C. No number. Magnesium formula key, Mg. No number. That's a giant structure. So if have approach to giant and simple. Okay, so coming back, that's what I try to say here. Let's see what I wrote. So simple molecular. What is so special about this chapter that bothers you? Focus on that. I think your main problem is you guys talk about this too much. The covalent bond. You don't talk about the covalent bond between the atoms when you're talking about their boiling points and melting points, because they all have low boiling points and melting points. If they all have low boiling points and melting points, the low boiling point can't be because of a strong covalent bond. So these forces are not broken during physical changes. If you think like bolbo na, it cannot bolbo. If I ask you, water boils at 100 degrees, which is a relatively low temperature compared to some other substances in the universe. Why? If you start off saying it has strong covalent bonds between atoms, you're saying because of the strong covalent bonds, it has a low boiling point. So if you're saying, now what if I want to write it just for the sake of it, to be safe? You're being silly, because if you say strong covalent bonds, then in the next line you'll have to say, but these are not important, or these have no effect. So why are you writing about something that has no impact on your observation? So you focus on this. They have weak intermolecular force. I mean, jor kore notes a force between molecule likhi, because I think chemistry students, especially younger chemistry students, hopefully you guys are not at that stage yet. But again, I don't have too much trust in the AS batch. Like everyone in the AS batch is thinking, it's a matter of just 3-4 months. 3-4 months ago, you guys were grade 10 students. It's not like suddenly something flipped in your head and okay, I became mature and A levels. 3 months ago, you were immature, and 3 months per you're saying you have a very sound knowledge of chemistry. I don't think so, because in fact, you've done less of this in the last 3 months. Your attention was more on key ionization energy. School teachers bothered you with mass spectrometry. They're bothering you with some other stuff that I'm not teaching you right now. Book 1, so organic chemistry. So you've actually learned, if anything, you've regressed in your knowledge of structures. So just be aware of this, okay? And this is the last time you're talking about all this with anyone, ever. Okay, so please focus on all this. So I intentionally say weak force between molecules, because I think chemistry teachers make this sound like some fancy term. Intermolecular money English force between molecules. They're all weak compared to the other forces. Okay. So however, within the molecule, there are strong covalent bonds inside the molecule. There are 3 types of intermolecular forces present between molecules. Read the previous chapter. Okay, so low properties, why? Low melting point, why? Because they have weak intermolecular force. This is not a good enough answer if you know the substance you're talking about. If I say, why does iodine have a low sublimation point? Its molecules are held together by weak London force. You be specific. Okay, so be specific to comment like so be specific with the name. You can't just write this. You're saying because I'm being generic here. I'm just giving you an overall answer. Be specific with the type of intermolecular force present in the example, in the question. So it's a simple structure. If you think, why do you have to write that? If they say in terms of bonding and structure, then you say it's a simple molecular structure. Not much energy is needed to overcome the forces. Poor electrical conductivity, none of them conduct electricity, even water, because there are no mobile electrons or ions or just charge carriers. Right. So water is the problem, because some people think panic, they switch to circuits, so little shock what is going on there, because the water you and I deal with every day is impure. So pure water is a very poor electrical conductor because it has very few ions, because this equilibrium lies far to the left. It doesn't ionize to a large extent. Okay, conductivity of water increases when you have dissolved ions present. That's what you have in tap water. Or most water that you drink or come in contact with, there are ions in it. If there were no ions, if it was 100% pure water, it would feel weird to us, because we've never had that. You've never drank pure water, and it would just feel weird to your taste receptors. Right. So next, water shows properties due to hydrogen bonding present in it that make it very useful in nature. It has a relatively high boiling point for a molecule its size with only 10 electrons. 100 degrees Celsius is pretty high. And that's vital to life on Earth, because it ensures that at these temperatures, you have liquid water on the planet, right? When it's this perfect temperature that we have for liquid water. And water not like there'd be no life on Earth the way we know life, because all these reactions happening inside you and me are happening in aqueous solutions, most of them. So much of us is water, right? So relatively high boiling point, which is higher than expected considering how small its molecules are. That's because of the hydrogen bonding, obviously. High surface tension and viscosity ignore korte paro. Physics se porle, you might want to link it. Did you learn this in physics? Not yet. So when they show you in physics books that like insects can skate on water, or you can, I don't know if you did this experiment, like I'm at a grade 10 physics, you can place a steel needle on water and make it float. Have you ever seen that? Okay, so if they teach you surface tension, usually physics teachers will use that example. Now, steel is denser than water, right? Steel should not be floating on water. So, if you think, why does it float? Very light objects, like a needle, it should still sink, first of all. Let's get that out of the way. It should still sink, even if it's a light object or mass to be common. But what happens with water is, at the surface, the molecules form like a stretchy active film, because they're so attracted to each other, right? So it's difficult to break through that barrier. So when insects skate on water, that's another one you'll see in physics books, like insects skating on water or standing on water. It's because the molecules are they're stretchy because they're trying to pull each other because of the strong hydrogen bonding. That creates like an upward force. like an upward force, which cancels out the force going down, right? So again, physics, chemistry, other AS nice, so I'd ignore this. And finally, right? Like biological importance of water একটা section থাকে না তোমাদের, এটা অনেকটা ওটার মতো লাগবে. Okay, and lastly, we'll end with this. Ice is less dense than water. So what do we know? What do we know about ice? It floats on water. As normal people, you know this, right? It floats on water. So it floats on water, because the density of ice is actually is less than water. Now that shouldn't be the case, because if anything, a solid should be more dense than its liquid form, because the solid particles are closer together. This is anomalous behavior. So this anomalous behavior happens because of the angle that water molecules need to achieve to form ice. What's that angle? They need to be aligned at 180 degree. I went for this kind of a diagram in the notes, right? But you're saying, what is the red dot? The oxygen. The white dot is the hydrogen. And this OH bond and the hydrogen bond with the lone pair has to be at an angle of 180. So if they are to align in that 180 degree arrangement, liquid molecules, they're moving around randomly in the liquid. But when they start to turn into solid, they need to all form that crystalline lattice. Very specific, that almost looks like diamond, tetrahedral arrangement. Like if you look at, this is another image I was considering putting in the notes for a dina, because you can always do a quick Google search for all this, okay? Like if you look at these images, this looks like diamond kinta. Looks very much like diamond. Okay, so if you look at crystalline structure of ice and you look at crystalline structure of diamond, almost same thing. So you're saying, so what are you saying? I'm saying you don't have to memorize this. Let me just end with this. You don't have to memorize this, but you need to know they have to have these very specific angles to form a crystalline lattice. So what ends up happening is you get this tetrahedral arrangement of water molecules, and in order to reach that perfect angle for the hydrogen bond, they can tend to take up more space. The water molecules liquid state because they're randomly moving around. But as they start to form solids, let's say they start to align, and it takes up a bit more. Like the way you arrange the molecules. That causes the volume of the water to increase. The volume of the water increases and the density therefore drops. Right? So you don't have to remember this. I'm writing this because most of you are physics. You probably saw this graph in physics as well. We call this the anomalous expansion of water. Or the unusual expansion from 4 to 0 degrees. So water reaches its highest density at 4, liquid water, which is unusual for a substance. Okay. So let me just read this and we'll wrap up. Usually solids are denser than their liquids, as the particles are more closely packed in solids. However, when ice forms, the water molecules, the phrase they'll ask you, take up a more open arrangement, which takes up more space or greater volume. This produces a rigid lattice in which the molecules are held in a tetrahedral arrangement. That would be my takeaway. Okay, so we'll end here. We'll finish off next on Monday, okay, on Wednesday. And তারপর workbook শুরু করব on Wednesday, okay? তোমাদের সাথে extra class schedule করছিলাম?